Hello everyone, welcome back to our course on abstract algebra. Today we're going to talk about what are permutation groups. So a permutation group is a special type of group, a finite group, but it's a very special type of group because, as we shall see later, there is a theorem that says that every finite group can be realized as a subgroup of a permutation group. So if we understood all permutation groups and all their properties, we could potentially understand the properties of every single finite group. So that's why they are so important. Also, they are important because a type of permutation group is that classifies the symmetries, the rigid motions of geometric figures. So because of the geometric application, these are very important. So let me start with an example of one such group. I want to talk about the symmetries of in this case, just an equilateral triangle. And just as a reminder again, what that is rigid motions of the triangle. So I want what motions will actually preserve the arrangement of sides, vertices, angles, distances, but so it will leave the shape, give me an equivalent shape, but there will be some motion of like where the vertices actually are. So for example, I can do something just very silly. I can do the identity map. That will be a rigid motion that leaves the triangle untouched. What else can I do? Something more exciting is that I can do from A, B, C, I can go to I can do a 120-degree rotation, and that will take A to this position, B will end up here, and C will end up there. I can also do something, I can do the 120-degree rotation twice and do a 200-degree rotation so that A will end up here, B will end up here, and C will end up here. What else can I do? There's also symmetries that are reflections. So if I start with A, B, C, I can reflect about this axis. And what that's going to do is that A is going to end up at the A position, but B and C are going to end up flipped. I can also, there are other such reflections. So I can do, let me draw A, B, and C. I can do a reflection about the B line or about the line that goes through C. And in this one, B will stay put. Here, C will stay put. In this one, A and C get permuted. And in this one, B and A get permuted. Okay, so what you can see is that actually, so this is reflection about A, let's call it RA. This is a reflection about B, and this is a reflection about C. Let's do a sub A. Whoops. So this is going to be called RA for a reflection about the line that goes by A. Okay, so I have now names for all of them. And what I want to see is that actually I can figure out which one of these it is by where the vertices go. So I'm going to, so I'm going to identify what is happening, but where the vertices go, basically, A is going to go to what position? For example, in the 120 degrees, A ended up at the B position, B ended up at the C position, and C ended up at the A position. So that is what we called a 120-degree rotation, is just sending A to B, B to C, and C to A to those positions. We are also, this same thing, I'm going to write a different type of notation. I'm going to write also like this, where is A going, where B is going, where C is going. So we're going to write that this is going to B, C, A. So I can actually write in that notation, I can write them all here ABC goes to ABC. Here's the one we just did. So ABC, A goes to the B position, B went to the C position, and C went to the A position. For the 240-degree angle, the 240-degree rotation, A went to the C position, B ended up at the A position, and C ended up at the B position. And similar now, A, B, C. In this one, you see A is definitely getting fixed, and C and B are getting permuted. In this one, it's B that gets fixed, and C and A got permuted. And in this one, what happened was that C got fixed, and B and A got permuted. Okay, we are going to also abbreviate these. So this is one notation, just as a function. This is another notation, and even simpler is that I'm just going to record where they go, that they went to, actually not quite like that. Look, what I'm going to write is the following notation, is that let's see where A goes in this, in the 120-degree rotation. I know that A went to B, and B went to C, and C went to A, so I'm going to write it as that cycle. And again, what this means is that A goes to B, B goes to C, and C goes to A. That's what this notation means. And this is a 120-degree rotation, or the equivalent of. Okay, so in that notation, what's the how do I write these? This one would go A goes to A, and that's it. B goes to B, and that's it. And C goes to C, and that's it. Or that is going to be just the blank permutation. There is nothing happening. This one, let me just write it in another place. So this one, the ABC goes to BCA in cycle notation. What I'm going to write is, let's say, where A goes, A went to B, B went to C, and C went to A. So in compact cycle notation, that is the way we're going to write that permutation. Let me write another one. So what happens with ABC, CAB? This was the 120-degree rotation. This is 240-degree rotation. This one I would write as A goes to C, C goes to B, and B goes to A. So in compact cycle notation, that's what it is. What about one of the reflections? So let's say the reflection about A, that is A goes to A, B goes to C, and C goes to B. How would I write that? I would write that A goes to A, so it's just a cycle of A going to A, and then B goes to C, which if it's a cycle that a letter is fixed, we don't even mention it, so I would just write BC. And similarly, the reflection about B will end up being, I know that B is fixed, and A goes to C, and C goes to A, so it will just be AC. Okay? So, again, what is happening, each one of these is just a permutation of the letters A, B, C. So I can go and define something more general, which is what is going to be a permutation group. So let X be a set of vertices, which in this case, I'm just going to number them 1 through n. Okay, and vertices or something that gets permuted, and then Sn, which is the nth permutation group. But everyone calls it just Sn, is the set of all bijections from X to X, where S is a bijection. Okay, so is that a group? Well, it turns out that theorem Sn under composition of bijections, so this is a composition of functions, is a group. It is a group, and we are actually going to call, we're going to count how many elements, and there is in fact n factorial elements. So it's a group that, you know, for n, it grows pretty quickly, the size of this group, because n factorial grows very quickly. So let me prove that the permutation group is in fact a group under composition. First of all, we need to know that Sn is closed under composition. So let F and G be elements in Sn, then F and G are bijections, and therefore F composed with G will be a map that goes from X to X and from X to X, first through G and then with F, and G composed with F in the other order will be also a map that goes from X to X and then to X, first F and then G, and composition of functions. First of all, if this is both F and G are bijections, then their compositions, if composed with G and G composed with F, are bijections. That's a property of bijections. You can check that because G is injective and F is injective, this composition will be injective, and because F is injective, G is injective, the composition will be injective. Surjective. G is surjective to here, F is surjective to here, so the composition will be surjective. So these are bijections. So that means that Sn is closed under composition. So that checks that that composition law works as a binary operation on Sn. Great. Now, what about, now we need to start checking the axioms of group. So let's check that G1, which is that the composition is associative. It turns out the composition of functions is associative. So since F composed with G composed with H is the operation we're talking about in Sn, so it will be that in the composition that we have, the operation we have is composition of functions, which is associative. This will be true for every F, G, and H in Sn. So we will have that the operation is associative. So that's the first axiom. Second, we need an identity element. And we do have an identity element because we have what I'm going to call identity. We have the identity that goes from X to X that sends every little x to itself. That was the identity permutation that we saw in the equilateral triangle that sent the triangle to itself, every vertex to itself. That is the identity element. And this works as an identity permutation of x because now if F is a bijection, then what is identity composed with F? Well, it will be for any x, it will be the identity of f of x. So if I compose the functions and see what function that is. This will be identity evaluated of f of x, which is f of x. And similarly, f composed with identity of any x will be f of the identity of x, which is just x. So in both cases, I get back f. So it works as a neutral element under composition. So that also works. What about the third axiom? We need inverses with respect to composition. So for any f from x to x, oh, by the way, I'm not sure if I said, but oh yes, x was a finite set, right? X was a set with n elements. So we do have finiteness. And for any f that is from x to x in Sn, since it's in Sn, f is a bijection from 1 to up to n, a finite set to itself, and therefore we have an inverse function because we have a bijection. We have an inverse. There is an inverse function to f that goes from x to x, such that well, the inverse function is that their composition is the identity. That's the property of an inverse function, of a set theoretic inverse function. And in both ways, the inverse gives you the identity. So those are the inverse elements that we need for a group, and therefore Sn under composition is a group. Great. So we have a group. Let's see then. Oh, we are not done. Let's not get ahead of ourselves, because there was something else in the statement, which is that there are n factorial elements. Now, let's count how many possible maps are there, bijections from x to x. Well, one is going somewhere, and I have complete freedom where one goes. There is n choices. Two, I have complete freedom, except that this has to be a bijection, so it cannot clash with my choice of where one went. So two, there are going to be n minus one choices for two up to n. And by the time I have to see where n goes, I've decided where 1 through n minus 1 went. So I've picked already n minus 1 elements are already picked out. So for n, there is exactly one choice. And if you put all of these together, there's going to be n times n minus 1 times 1 choices of bijections x to x, and therefore Sn, which is the set of all bijections from x to x, has this much, which is n factorial elements. And now I am done. So Sn is a group, and it has n factorial elements. Let's see an example. Oops. Let's see an example with n equals 3. So I'm looking for bijections from 1 to 3 to 1 to 3. And I'm looking for all such bijections. Then S3 are, well, the possibilities are 1, 2, 3 goes to 1, 2, 3, that is the identity. Then 1, 2, 3 goes to, let's keep 1 fixed, and if 1 is fixed, then the other possibility is that 3 and 2 get permuted. And then let's suppose now 1 goes to 2. If 1 goes to 2, then 2 can go to 3 or to 1. So there is the one that goes like this, or 1, 2, 3, and 2, and then 2 goes to 3, and 3 goes to 1, right? then that exhausts the possibilities of 1 going to 2. So now there is the possibilities of 1 goes to 3. And if 1 goes to 3, then 2 can go to 3 or to 2. 2 can go to 1 or to 2. So if 2 goes to 1, then 3 went to 2. And if 2 goes to 2, then 3 went to 1. And that actually exhausts all the possibilities of S3. So there is 6 elements, so there are 3 factorial elements. This is all of S3. In my compact notation, by the way, S3 is, we have the identity element, so just 1 goes to 1, or if you want the empty cycle, everything goes to itself. Then the second element, 1 is fixed, but 2 goes to 3 and 3 goes to 2. So in compact notation, the second element is 2, 3. In this third element, let's see, 1 went to 2, 2 went to 1, but 3 got fixed, so that's it. The third element, 1 goes to 2, and 2 goes to 3, and 3 goes to 1, so it closes the cycle. In this one, 1 in the fifth element, like the movie, 1 goes to 3, and then 3 goes to 2, and 2 goes to 1, so that closes the cycle. And in the sixth element, 1 goes to 3, 3 goes to 1, so it closes that cycle, and 2 goes to 2. So these are all the possible elements in S3. Okay, very good. Let's see, though. We proved that Sn is a group, but we didn't say anything about whether it's abelian or not. So let's show that actually it is not abelian, even in the case of S3. So let's prove that Sn is not abelian in general. So let's take again the case of N3 and see what happens if I compose the map that goes to this map composed with this one. So if I compose this way, let's see what is happening. I can, so first, this one is the first one to operate on numbers, and then this is, so this goes first and this goes second. So let's see what is happening. 1 with this one goes to 3, and then this one, the second one, sends 3 to 2. So 1 was going to 2 after all. 2 goes to 1 first, and then 1 goes to 1. So 2 goes to 1. And 3, through the first one, 3 goes to 2, and then 2 goes to 3. So overall, this one is 1, 2, 3 is 2, 1, 3. Okay. But what about, by the way, in compact notation, this is the cycle 2, 3 composed with the cycle that goes, let's see, 1 goes to 3 and 3 goes to 2. So if I compose these ones, what I can do is just check first 1 goes to 3 in the first one and 3 goes to 2. So that tells me that 1 went to 2 overall. And now I can see where's 3 going, or where's 2 going, since I need to know now what's happened to 2. 2 goes to 1, and 1 is fixed, so 2 goes to 1. So this closes this cycle. And then let's see what happened to 3. 3 goes to 2, but 2 goes to 3, so 3 is stable. 3 stays put. So that is just 1, 2, which is the same permutation that is represented by that other notation. Okay, let's see what happens then if I go the other way, 1, 3, 2 composed with 2, 3. Then let's first see where 1 goes. 1 stays put here. This one doesn't do anything to 1, so 1 goes to 1. And here 1 goes to 3. So 1 goes to 3. Let's see where 3 goes. 3 goes to 2 here, and 2 goes to 1. So 3 goes to 1 overall, so it closes this cycle. And then what happened to 2? 2 goes to 3, and 3 goes to 2, so 2 stays put. So this one is actually 1, 3. And then you can see that these are not the same operation. So these are not the same symmetries or the same bijections, and therefore composing 2, 3 with 1, 3, 2 is not the same as composing 1, 3, 2 with 2, 3, and so S3 is not abelian. It's not commutative. Okay. Let's see some more examples of working from one notation to the other. So let me give you a large permutation. So I'm going to look at the permutation that is 1, 2, 3, 4, 5, 6, 7. So this is some element of S7. And this is doing the following permutation. 1 goes to 6, 2 goes to 3, 3, 5, 1, 4, 2, 7. To be a permutation, I have to have every number from 1 to 7 down here, and only once. So you see this is a permutation. It's telling me where everything goes. So I want to write this in compact cycle notation. So let's see where 1 goes. I start with 1 and see where it goes. 1 goes to 6. Okay, now I look at 6 and see where 6 goes. So 6 goes to 2. Then I look at 2 and see where 2 goes. 2 goes to 3. 3 goes to 5. 5 goes to 4. And 4 goes to 1. And since that's where I started, I close the cycle. What am I missing? I have 6 numbers here, so I have to see where 7 goes. And 7 goes to itself, so it's a little cycle by itself. Which again, we usually in this compact notation, we do not write down. So this is the cycle 1, 6, 2, 3, 5, 4 in S7. Let me do another example of this, 1, 2, 3, 4, 5, 6. This time in S6, this is a permutation that goes to 2, 4, 1, 3, 6, 5. I want to write it in compact cycle notation. So in compact cycle notation, I start with the 1. Let's see where 1 goes. 1 goes to 2, then 2 will go to 4. So 1 goes to 2, 2 goes to 4, 4 goes to 3, and 3 goes to 1, so it closes the cycle. Now I have 1, 2, 3, and 4. So what's the next number? Let's see where 5 goes. 5 goes to 6, so it's not going to itself. And 6 goes to 5. So 1, 2, 3, 4 is, so this permutation in compact cycle notation is a product of 2 disjoint cycles. Okay, this is a cycle of order 4, and this is a cycle of order 2. What else? Let's also see how to do products or compositions of products of cycles. So what happens if I do, I'm going to multiply 1, 2, 3, 4, 5 times 3, 5, 6. How do I figure which one is this? You see there is some intersection. While these were disjoint cycles, this tells me where 5 and 6 goes. 5 and 6 are fixed here, while 1, 2, 3, and 4 are fixed here, and this tells me where 1, 2, 3, and 4 goes. So this is what we call a product of disjoint cycles. But this is a product, but they're not disjoint. So I want to write it as a product of disjoint cycles. So I'm going to do like I've done before. I'm going to start, let's see where 1 goes. 1 goes to 2. Okay. 2 is fixed here, but 2 goes to 3 here. So 2 goes to 3. Now I see that 3 goes to 5 here. And then 5 goes to 1. So 3 goes to 1 overall, and it closes this cycle. Great. Now I go for the next number that I haven't touched yet. which is 4. 4 is fixed here, but 4 goes to 5 here. Great. So where does 5 go? Let's see. 5 goes to 6, and 6 stays put, so 5 goes to 6. Now where does 6 go? 6 goes to 3, and 3 goes to 4, so 6 goes to 4, and that closes this cycle. And now I have where every number goes, 1 through 6. So this is now what was a product of not disjoint cycles. Now I have written it as a product of disjoint cycles. And products of disjoint cycles are great because those commute. We're actually going to show in a moment that those commute, but let me show you that product of cycles that are not disjoint, they do not commute and make things more difficult to work with. So let's see actually that the product of two cycles, I'm going to multiply them in two ways, that those do not commute. So what is this product? 1 goes to 3 and 3 stays put here, so 1 goes to 3. Now 3 goes to 1 and 1 goes to 2, so 3 goes to 2, and then 2 stays put here and 2 goes to 1, so 2 goes to 1, and it closes this cycle. What is this product now? 1 goes to 2 and 2 stays put, so 1 does go to 2, and then 2 goes to 1 and 1 goes to 3, so 2 goes to 3, and 3 stays put here, but 3 goes to 1, so 3 goes to 1 and closes the cycle, and then you can see that these are not, this is not the same. However, as I said, let's prove a lemma that says let sigma and tau be disjoint cycles in Sn, then sigma composed with tau is the same as tau composed with sigma. So let's prove that disjoint cycles do commute. So let sigma and tau be in Sn and disjoint. What that means is that if sigma of I is j, which is not I, then tau must leave I alone. Okay, and tau of j must be j. So if sigma does something to I, then tau must do nothing to I, essentially. So let's suppose that sigma does do something to an element I, okay? And let's see what is sigma of tau of I. That tau leaves I alone, so that is sigma of I, and sigma of I is j. Let's see what tau composed with sigma composed with evaluated I, what does it do? Sigma does do something to I, it sends it to j, but tau cannot touch j because there are disjoint cycles, so j is j. And then you see that these are actually the same, so they work exactly the same. Similarly, if tau does something to another number, and if tau permutes k, we send it to some r, then sigma cannot do anything to that k on r, and the same behavior happens then, that they are going to be the same. So you actually get those two are going to commute. And finally, I want to show that what we've done here, so this process that I did here, a product of not disjoint cycles, any cycle, I've been able to write it down, any permutation, I've been able to write it down as products of disjoint cycles. So let's prove that that is actually the case, and that every permutation, every element of Sn can be written as a product of disjoint cycles. So let's prove that. What we've done to prove this in practice is to start with 1, see where 1 goes, find a cycle, and then just put that as 1 cycle. Then find some other number that was not touched previously by the cycle that did not appear in the cycle of 1, and go with that. So that is exactly what I'm going to do. So let sigma in Sn be arbitrary, and consider, well, I have sigma of 1, and then I'm going to look at sigma of 1. So where 1 goes, then where 1 went, where does that go, and so on, up to, I just apply sigma many times, okay, like that, and suppose this is what I'm going to call sigma k of 1, so this is sigma applied sigma k times, okay? Since x, which is 1 through n, is a finite set, we have to have a repetition in this list. So this is a list of like where 1 went. This is a list of where 1 went, and then where, if 1 went to something, where did that go, and so on. So this is a list of elements of x. And since x is finite, at some point we're going to hit a repetition. So there is a repetition in the above list. And what that tells me is that there is some n bigger than k such that the nth iteration of where 1 goes is the same as the kth iteration of where 1 goes. And since this is a group, I can actually multiply both sides by the inverse of sigma to the k. So that is sigma to the n minus k of 1 is 1. And I'm going to call that this number n minus k, I'm going to call it k1. So the first repetition of 1 is at the n minus kth place. So I have 1, then sigma of 1, where 1 went, and so on up to the sigma n minus k minus 1 of 1. And then this tells me that the fact that the n minus k iterate of 1 is 1. After this one in the cycle, in the compact cycle notation, this is going to go back to 1, so the cycle closes. So I have 1 cycle. This is a cycle, which is like the cycle of 1. Okay? And now just take a number that is not in this list and do the same. Start with I, sigma I, and so on. So let I be in x, but not in x1. Okay, so the numbers that are in here, I'm going to call that x1, the set with all those numbers. So take some number that does not appear in the cycle and do the cycle of that number. So now consider I, sigma I, and keep going up to some sigma k2 minus 1 of I, such that I hit, after that, I will hit I again. So, and then sigma k2 of I is I again. There will be a repetition at some point. And then what that tells me now is that I can create, so I set x1, this will be the set x2 of numbers, and so on, a set of numbers, such that, so keep going like this until you have all of x is in x1. Disjoint union, I'm going to write this symbol, which means disjoint union of x2, disjoint union all the way up to xm, and I am done. Then I am done, and I can actually write my cycle sigma as a product of cycles, because now if I write, if I define sigma j of x to be just sigma, what sigma does to x, if x is in xj, and fix every other element that is not in that subset, then sigma will be a product of sigma 1, sigma 2, sigma m. And those, because all the numbers are, the numbers that are involved in here are the x1s, the x2s, and the xm's, and each one of those is disjoint, all those sets are disjoint, then sigma is a product of disjoint cycles, which is what I wanted to prove. And therefore, I can write every cycle as a product of disjoint cycles, just like we've done several examples, but let me do another one. For example, what is 1, 2, 2, 3, 3, 4? Those are not disjoint. Let's write it again as a product of disjoint cycles. I start with 1 and do my x1 subset. So where does 1 go? Let's see, 1, fixed, 1 goes to 2, so 1 goes to 2. Where does 2 go? 2 goes to 3, and then 3 is fixed, so 2 will go to 3. Where does 3 go? 3 goes to 4, and 4 is fixed, so 3 goes to 4. Where does 4 go? 4 goes to 3, 3 goes to 2, and 2 goes to 1, so 1 goes to 4 goes to 1, and it closes the cycle. And actually, I'm done. I don't have any other numbers. So it is a product of disjoint cycles. It is exactly one cycle. So we'll see in the next video that actually this decomposition is useful. This is a decomposition of 1, 2, 3, 4 of one cycle as a product of what we call transpositions. And that is something that comes up in the theory. So I'll stop here. And in the next video, I'll talk about transpositions, products of transpositions, and what we call the alternating group.